Hello everybody, welcome back. In previous video we have discussed Mendeleev's periodic table. There are many limitations in Mendeleev's periodic table. After Mendeleev, in 1913 H.J Mosley discovered the number of positive charges or protons present in the atom of an element with X-ray experiment, and these positive charges or number of protons called as atomic number. The atomic number is nothing but the number of positive charges or protons present in the atom of an element. After knowing the atomic number, it was recognized that a better way of arranging elements in the periodic table, that is according to increasing order of atomic number, and this arrangement eliminated all the limitations of Mendeleev's periodic table. For example, anomalous series. Here in the Mendeleev's periodic table, tellurium is arranged before iodine, even though tellurium has more weight than the iodine. The atomic weight of the tellurium is 127.6 units, whereas the iodine has 126.9 units. So here the tellurium is placed before iodine. So this arrangement, placing the higher atomic weight atom before low weight element, is said to be anomalous series. So after knowing the atomic number, it was recognized that the atomic number of tellurium is 52, whereas the atomic number of iodine is 53. If we arrange these elements based on atomic number, then it is clear 52, the tellurium comes first, then the more atomic number, that is 53 of iodine. So this type of limitations have been eliminated from the Mendeleev's periodic table after knowing the atomic number. Later, the periodic law also changed from the concept of atomic weight to atomic number. According to Mendeleev's periodic law, the properties of elements are periodic functions of their atomic weights. The modern periodic law states that the properties of elements are periodic functions of their atomic number, and based on this modern periodic law, the new arrangement of elements was done, and this new arrangement of elements are known as modern periodic table. And Mendeleev's periodic table is said to be short form of periodic table, and whereas the modern periodic table is said to be that long form of periodic table. There are total 18 vertical columns in the modern periodic table. These vertical columns are known as groups, and similarly 7 horizontal rows are there in the modern periodic table. These horizontal rows are said to be periods. So total 18 groups and 7 periods. So then what decides the position of elements in the modern periodic table? Just before we have discussed that atomic number decides the position of an element in the periodic table. So here the atomic number is nothing but the number of protons. If the atom is neutral, then in that the same number of electrons also present. For example, let us take sodium. The atomic number of sodium is 11, which means 11 protons are present in the sodium. So if the sodium is neutral, there is no positive charge or negative charge. So same number of electrons also present in that sodium. Then the position of the sodium mainly decided by its electronic configuration, the arrangement of electrons in the subshells, and orbitals. Then how these electrons are filled in main shells and subshells. In previous videos we have discussed the filling of electrons in main shells and subshells and orbitals. Check the I button to get idea about the filling of electrons in the subshells and main shells. Then how these electrons are filled into that main shells and subshells. So for example, first shell is said to be K and it has only one subshell, and S subshell has only one orbital, and this orbital, each orbital can hold 2 electrons. We can accommodate 2 electrons in each orbital, and so the maximum number of electrons we can fill in the first shell is 2. 2 electrons only we can fill in the first main shell. Then come to second main shell, that is L, and here 2 subshells are there, S and P, and S subshell has 1 orbital and P subshell has 3 orbitals, that is nothing but Px, Py, Pz. So each orbital can hold 2 electrons. So S subshell can hold 2 electrons and P subshell can hold 6, Px2, Py2, Pz2. Total 8 electrons we can fill in the second subshell. And similarly, M main shell, and it has 3 subshells, S, P, D. S has only 1 orbital, P has 3 orbital, and D has 5 orbitals. So in S orbitals 2 electrons, and in P subshell we can fill 6 electrons, 3 into 2, each can hold 2 electrons, and in D subshells 5 orbitals are there, so each one can hold 2 electrons, so 5 into 2, 10 electrons. How many electrons we can place in the main shell, third main shell? That is nothing but 10 plus 6, 16 to 18 electrons. Similarly, N main shell. N main shell has 4 subshell, these are S, P, D, F. In S orbital only one orbital is there, in P subshell 3 orbitals, in D subshell 5 orbitals, in F subshell there are 7 orbitals. So here 2 electrons in S, here 6 electrons in P, here 10 electrons in D, and 14 electrons in F. So in this way we can fill the number of electrons present in an atom and main shell and subshells. So then this is the way of writing the electronic configuration. To get full idea about filling the electrons in that main shells and subshells, check the I button and watch that video, you will get clear idea. So now based on this, let us try to write the electronic configuration of the sodium. So 11 electrons are there in the sodium, then 2 electrons, first 2 electrons filled into first main shell and subshell S, and subshell can hold 2 electrons. Then only one subshell is there in first K shell, first shell, so only 2 electrons are filled. Still the sodium has 9 electrons. Then the electrons enters into S orbital of second main shell, L main shell. So 2 electrons, and here P orbital also there in second main shell. So how many electrons we can fill in the P orbital, P subshell? Total 6 electrons in Px, Py, Pz. So total in second main shell we can fill 8 electrons. So 6 plus 2 plus 10 electrons are there, and still one electron is there in the sodium. So that last electron enters into the S orbital of third main shell, M shell. So this last electron decides the position of elements in the modern periodic table. So this electron is also said to be differentiate electron. This differentiate electrons decides the position of element in the modern periodic table. So here that sodium belongs to first group, and the main shell decides, the outermost shell decides its period. So this sodium belongs to third period and first group. So the outermost electron into which orbital it has filled, that decides its group, and that outermost shell decides its period. So here sodium belongs to third period and first group. Let us take one more example. Let us take that nitrogen. Its atomic number is 7. The number of protons in the nitrogen is 7. Then same number of electrons are there. Then its electronic configuration 1s2, 2s2. So 4 electrons are completed, 2p3. So here in the last outermost shell in the nitrogen is second main shell or L shell. And how many electrons are there in the second shell? In s orbital 2 electrons, in p orbital it has 3 electrons. So the group of the nitrogen is fifth group. Fifth group, or generally it is called as fifth A group. Fifth A group. This nitrogen belongs to fifth A group, and the outermost main shell is 2 in the nitrogen, so it belongs to second period. Similarly, one more example here. Let us take that calcium. The atomic number of calcium is 20. Its electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. So here in the third main shell there is 3d orbital also there. So while filling the electrons in the subshells and orbitals, we need to follow the Hund's law, Pauli's exclusion principle and Abbo's principle. According to Abbo's principle, the low energy orbital is filled with electrons first. So here after 3p there is 3d, and also in fourth shell 4s. So here which one has the low energy? The electron, the last 2 electrons are 18 electrons are already filled. The last 2 electrons have to fill the low energy orbital. Here how we decide the low energy orbital? So it is simple, that is nothing but n plus n value gives the low energy orbital. Here n is nothing but that principal quantum number or the number of main shell, and L is angular momentum. So angular momentum quantum number depends on n. So here this is the main shell for d orbital, 3 plus L values are starts from 0 depending on n. So 0 to the maximum L value is n minus 1. So 1. So if L equal to 0, that is s orbital. If L equal to 1, then that is p orbital, and if L equal to 2, that is d shell. So here the d orbital, the L value for the d orbital is 2. So that 5 units of energy 3d orbital has. And here similarly it's a main shell of 4s orbital, and L is nothing but 0 plus 0. So its energy is 4 units. So the 3d orbital has higher energy than the 4s orbitals. So that's why according to Abbo's principle, before filling the electrons into 3d orbitals, the electrons are filled into s orbital of fourth main shell. Then what is the group and what is the period of this calcium? So here that s orbital, in s orbital there are 2 electrons. So that calcium belongs to second group. So second group, and its period outermost orbit is 4th orbits, then it belongs to 4th period. So this is the position. This decides the outermost electronic configuration, decides the position of elements in the modern periodic table. The modern periodic table has been divided into 4 blocks. So that is S block and P block, D block and F block. So how we decides these blocks? So this is simple. The outermost electronic configuration decides block of elements. For example, sodium, its atomic number 11, then aluminum, its atomic number is 13, scandium, its atomic number is 21, and cesium, its atomic number is 58. Now let us write the electronic configuration of these elements. First 1s2, 2s2, 2p6, 3s1, total 11 electrons in the sodium. Then aluminum 1s2, 2s2, 2p6, 3s2 and 3p1. And here scandium 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. After filling 4s, the electrons enters into d orbital. Similarly, for the cesium 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 5s2, 4d10, 5p6, 6s2, 5d1, 4f2. So here, and modern periodic table is divided into 4 blocks, mainly based on the outermost electronic configuration of the elements. So here sodium, it is last outermost orbital is s orbital. So this is s block element, and here the aluminum having outermost orbital p. So it is ending with the last electron is filling in the p orbital. So that aluminum is belongs to that p block element, and scandium outermost electron is filled in d orbital. So it belongs to d block element. Similarly, in the cesium, the outermost electrons filled in the f orbital. So these elements are belongs to f block elements. So in this way, based on the filling of the electrons in outermost orbit, that modern periodic table has been divided into 4 block: S block, P block, D block and F block. So then what are groups? Let us learn clearly about groups and periods. In the modern periodic table, 18 vertical columns are there. These vertical columns are known as groups. In traditional notation, these are represented with 1 to 8 with Roman numbers and with A and B series. So in A series elements, that all elements of S block and B block elements comes 1A to 8A series, and the D block and F block elements comes under 1B to 8B elements. So this is the traditional notation, and but according to latest recommendations of IUPAC, now all the groups are represented with Arabic number from 1 to 18, and the elements in one group having same outermost configuration, electronic configuration. For example, let us take the first group elements: hydrogen, next lithium, sodium, potassium and so on. So here the atomic number of hydrogen is 1 and lithium is 3 and sodium is 11 and potassium is 19. Let us try to write its electron configuration. 1s1 and second one is 1s2, 2s1 for lithium. For the sodium, 1s2, 2s2, 2p6, 3s1. Similarly, for the potassium, 1s2, 2s2, 2p6, 3s2, 3p6 and 4s1. Here, if you observe the outermost electronic configuration in hydrogen, lithium and sodium, potassium. So, last electron, the final electron or differentiate electron ended leaving one electron in s orbital. So, the outermost electronic configuration decides its group number. So, these all elements are belongs to the first group elements and they shows similar properties. So, they all having similar properties because they are showing similar properties because having the same electronic configuration. So, S1 this decides that group, and these elements in one group are said to be the elemental group or chemical group. Okay, they shows similar properties because of having same outermost electronic configuration. For example, if you go for second group, so all the elements having similar properties. Ns2, the last electron is second electron, outermost electron, differentiating electron is second electron in s orbital, 3s2, 4s2, 5s2, so on. And if you go for third A group or 13th group, so that is ends with ns2, np1. So these are the 13th group elements or third A group element. So in this way, the each group shows its a special characteristic of properties because of having the same outermost electronic configuration. Each group of elements have been given the special names. For the first group elements are said to be alkali elements, and second group elements alkali earth metals, and third group elements boron family, nitrogen family, carbon family, and halogens, chalcogens and noble gases. In this way, each group elements shows their own properties, and these are said to be element family or chemical family. Next come to periods. In the what factor decides the period of an element? It is simple. The outermost shell, main shell decides its period. For example, sodium already we have discussed. Its atomic number is 11, 1s2, 2s2, 2p6, 3s1. What is the outermost orbit for the sodium? The last electron is filled in third main shell, so the sodium belongs to third period. And potassium 19, sodium potassium belongs to same group but their periods are different, 2p6, 3s2, 3p6, 4s1. So that potassium belongs to fourth period because it has outermost shell, fourth outermost shell. So both belongs to first group, okay, because both having similar outermost electronic configuration. So outermost orbit decides or main shell decides the period of the elements, and there are 7 horizontal rows. These horizontal rows are said to be periods, and each period start with s orbital and ends with p orbital. In between there may be f orbital and d orbital. In first period only 2 elements are there, and they are 1s1 hydrogen and helium, and ends with helium, that is with electronic configuration S2, and the main shell is only one, that is K equal to 1 first period. Similarly, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. They have two main shell in them, two main shells. So for example, the lithium, atomic number of lithium is 3, so 1s1, 1s2, 2s1, and beryllium, its atomic number is 4 and 1s2, 2s2, and here boron, atomic number is 5, 1s2, 2s2, 2p1. Similarly, carbon is 6, so 1s2, 2s2, 2p2, and nitrogen is 7, its electron configuration 1s2, 2s2, 2p3, and oxygen, its atomic number is 8, 1s2, 2s2, 2p4, and fluorine, its atomic number 9, 1s2, 2s2, 2p5, and similarly the neon, its electronic configuration 1s2, 2s2, 2p6. If you observe all these 8 elements, so they all belongs to second main shell or second period, because they having two main shells in that. So the outermost shell decides. Here all these all are having second shell, so it divides. Outermost orbit in the element decides its period. So in the first period there are only 2 elements, and in the second period there are 8 elements from lithium to neon, and in the third period again they have 8 elements from here hydrogen to helium, and here lithium to neon, and in the third period how many elements are there? 8 elements from sodium to argon. In fourth period 18 elements are there from potassium to krypton, and fifth period 18 elements are there rubidium to xenon. Total 18 elements. In this, S black 2 elements and P black 6 elements, and D black elements are 6. And next sixth group element, that total it has 32 elements from cesium to sixth group element. Sixth period has total 32 elements from cesium to radon, and seventh period is that incomplete, because still some elements have to be discovered. So in this way the elements of first period has only one shell, K shell, the first shell, that's why they belongs to first period. Similarly, the second period elements from lithium to neon, they have the first shell as well as outermost shell in them. In 8 elements lithium to neon, they have that second shell, second main shell. So 2 shells they have, that's why they belongs to second period. Similarly, third period elements, 8 elements are there, sodium to argon, these all are having that the outermost shell KLM, okay, inner 2 shells and outermost shell M shell. So 3 shells are there, that's why these elements belongs to third period. Similarly, the elements of fourth period from potassium to krypton, they have K, L, M. Then outermost shell N, fourth shell N, that's why they belongs to that fourth period. So here 2 S black elements and 6 P black elements, total 8, and 10 D black elements. From fourth period D black elements come into order in fourth period. Okay, there are 10 elements of D black elements in the fourth period, and fifth period also having the 18 elements from rubidium to xenon. So they have K, L, M, N, and outermost shell is O. So 5 shells are there, that's why these all elements having 5 shells, they belongs to fifth period. 2 elements, total 18 elements, 2 S black elements, 6 P black elements, total 8, and 10 D black elements. So 2 plus 6 plus 10. So each period starts from S black elements and ends with P black elements. In between them, P black and S black and P black, there may be D black and F black elements. So then come to sixth period, and there are 32 elements from cesium to radon. So they have K shell, M shell, L shell, M shell, N, and O, and P. So 6 main shells are there, that's why these 32 elements having 6 shells, that's why they belongs to sixth period. 2 S black elements, 14 F black elements, 10 D black elements, and 6 P black elements. So total 32 elements are there in that sixth period. So in this way, each period starts from the S black elements and ends with P black elements. So seventh period is incomplete. So main shell, outermost shell is seventh shells. 7 shells are there in the elements present in seventh period, but this seventh period is incomplete because the number of elements not yet discovered. So that is incomplete. To be the D black elements are said to be transition elements, and that F black elements are inner transition elements. The F black elements kept separately because if they keep in the long form of periodic table, that periodic table will very long. F black elements show similar properties like lanthanides and actinides in D black elements, that's why they are also said to be lanthanides and actinides. So and they kept separately at the bottom of the long form of periodic table. So this is about that modern periodic table of elements. So in next class we will discuss the properties of elements and the factors which affecting the ionization energy. Thank you.